Esteemed viewers, in this tutorial we discuss dynamic programming algorithm design strategy. Dynamic programming is a famous algorithm design strategy which has interesting history. It was invented by the prominent US mathematician Richard Bellman in 1950s. It was designed as a general method for optimizing multistage decision processes. Thus, the word programming here doesn't mean programming using some high-level language. It doesn't come in that parlance. Instead, programming here means way of thinking or planning for problem solution. Planning for problem solution. Therefore, there is no programming per se, and it is used in mundane terms. Generally, in our mundane life also, we will be talking something like schedule a program for some discussion, schedule a program for a visit, something like this. It comes in that particular parlance. Programming here means planning to obtain the solution, and this particular technique is specially applicable for designing algorithms for optimization of objective functions. It is also suitable for problems with overlapping subproblems or overlapping solutions of the same type. Of course, the solution is progressively obtained by making use of the previous solution. That means every problem that can be dealt under dynamic programming concept will have some kind of initial solution, and we will be making use of these initial solutions to progress towards the solution for the whole problem. That is the idea of dynamic programming. As a first example, we can quote Fibonacci numbers, generation of Fibonacci numbers up to a given term. And all of us know that it will start from 0 and it will have 1. These are all the two initial values that is to be supplemented with, and these initial values should be used, and f of 0 plus f of 1 will be the first term. First term is 0, second term is 1, and the third term is obtained by adding these two terms. Okay, exactly speaking, this should also be 1. Okay, 1, 2. Yeah, now it's correct. Okay, so 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, so 3 plus 2, 3 plus 2, 2 plus 3 is a overlapping solution for the term number up to 5, it is 3. Then if you want to increase the term numbers, you have to add these overlapping solutions. In general, we can write a recursive simple recurrence relation, f of n equal to f of n minus 1 plus f of n minus 2, of course, for the values of n greater than or equal to 2. That means up to 2 terms is readily available, and these 2 terms or 2 answers or 2 solutions will be made use to develop the further solutions. Of course, therefore, Fibonacci numbers or generation of Fibonacci numbers has the two initial conditions, f of 0 equal to 0 and f of 1 equal to 1. And the bone of contention in this particular discussion is to develop an algorithm for finding binomial coefficients. Okay, binomial coefficients is a standard example, I should say. It is a standard example of dynamic programming to a optimization problem, for a non-optimization problem, of course. A plus b to the power of n. Okay, here binomial coefficients will appear as a multiplicative coefficients for the expansion of binomial series or binomial formula. A plus b to the power of n is nc0 a to the power of n plus nc1 a to the power of n minus 1 and b to the power of 1, etc., nck a to the power of n minus k b to the power of k and ncn b to the power of n. The coefficients will go on increasing and it will be NCN, and here the first term will have the nth power and the second term will have 0th power. Progressively the power of the first term will be decreasing and the power of the second term will be increasing. Ultimately the second term will reach to the power n, first term will have lost and it would have become to the power of 0, a to the power of 0. Therefore this can be definitely recalled very easily, but the problem is how to generate these particular values. Okay, in some other circles NC0 is connoted as combination of n items selecting 0 at a time, and NC1 is combination of n items selecting 1 at a time. Therefore binomial coefficients in other way means combinations. It's not so unlike so it's a pertinent point to recall our attention or recall our memory to bring out the difference between combination and permutation. If you have only two items, permutation of two items, say A and B, is AB and BA. It is 2 factorial. And as far as combination is concerned, AB, that is the only one combination. BA doesn't hold water. Anyway, both of them are present, A and B are present, that makes combination. It is combining items, it is choosing the items. But whereas permutation is arranging the items. The positional value or the position of each and every element also matters in case of permutations. Therefore, for a given n value and k value, there will be much more permutations than combinations. This is a salient difference between permutation and combination. Anyway, the point of discussion is how to evolve or how to generate these binomial coefficients that will appear in the binomial expansion of this term. Okay, and therefore, but there are two important, among several important features about this numerous properties of these binomial coefficients. We quote here the related ones which are very useful in the context of dynamic programming. That is, NCK can be expressed as n minus 1. Of course, n is very much greater than k or k is very much lesser than n. Then only it will carry some kind of a meaning. Okay, NCK can be expressed as n minus 1 into C of k minus 1 plus n minus 1 C of k for values of n greater than k and k greater than 0, and NC0 equal to NCN equal to 1. These are all the known things. Okay, and we can take an example to find combination or this coefficient for an arbitrary value like 4C2. So 4C2 can be expanded something like this using this formula. So 4 minus 1 3, 2 minus 1 1, 4 minus 1 3 and 2. That's what it is written. 3C1 plus 3C2 using the first formula. Okay, this is the first characteristic feature. We can just name this. We can just number this for the purpose of clarity. For the purpose of clarity, we will just number this. Okay, this is 1, this is relation 1, and this is relation 2. Okay, this is solution only. Solution comes in a particular form, and making use of these solutions, we will just overlappingly use these solutions to generate the next solution. That is the intent. So 3C1 plus 3C2 according to the formula number 1, and 3C1 can be expressed as 3 minus 1, that is 2, and 1 minus 1, that is 0, 2C0 and 2C1, and this can be expressed once again as 2C1 plus 2C2. So 2C0 is 1 according to the second formula. Okay, 2C0, NC0 and NCN, 2C2, something like that. So 2C0 is 1 and 2C1 can be expressed as 1C0 plus 1C1, and 2C1 can be expressed as 1C0 plus 1C1, and 2C2 is 1. 2C2 is 1 because it is analogous to NCN. Okay, so this is 1, 1C0 is 1, 1C1 is 1, and 1C0 is 1, and this is 1, and this is 1. Put together, the complete answer is 6. 4C2 is 6. Do we need such a drudgery? Yeah, it is needed, because if at all we want to expand a binomial series, binomial expansion, Okay, we need to write these coefficients. Okay, we cannot do some kind of an arithmetic like this, something like this. This involves huge calculation. NCK can also be expressed as n factorial divided by n minus k factorial into k factorial. That is 4 into 3 into 2 factorial divided by 2 factorial into 2 factorial. It will cancel away. So 4 into 3 is 12 and 2 factorial is 2. So 12 by 2 is 6. This is what we got. But this involves huge calculation. Therefore, expansion is little better. As a solution, there is a simple method for calculating combination of anything. Let us take an example of 7C3. Let us say 7.3 need to be calculated, and there is a method which is available wherein we progressively develop some kind of a solution. Okay, this is simplest method. We apply the formulas, two formulas that are presented, formula number 1 and formula number 2, which is characteristic feature of two features of binomial coefficients. So 0 n goes this way, vertically down, okay, and k goes this way. So both of them can start from 0, k from 0 to k, and n from 0 to n. So k will also come in between because k is always lesser than n. Okay, so 0, 0, C0. This is how we are supposed to read. Of course, by the by, combination can also be expressed as some people will write something like this, n k. This is also another way of expressing the combination. Okay, we have used this particular convention, that is n c k. Or there is another convention wherein the combination can be expressed as C of n comma k. Anyway, all the three notations, all the three representations mean only one thing, that is combination. Combination of k items, combination of n items, choosing k at a time. Okay, now we will proceed to this. Okay, 0, C0, 1. Okay, this is analogous to NCN. 1 C0 is 1. 1 C1 is also 1. Now 2 C0 is 1. Now we need to calculate 2 C1. For this, there is a simple method that is being devised. We need to write the answer over here. We need to expand somewhere over here, and we will see the entry immediately above that particular column, on the column. So that is 1, and we will also see the entry behind in the column preceding column, and we will add this. I repeat, it is essential to see the entry in the column above this particular number and the preceding entry. So this is 1 and this is 1. So 1 plus 1 is 2. And now it becomes 2C2. 2C2 is 1. Similarly, 3C0 is 1. Then 3C1 is 2 plus 1, that is 3. 3C2 is 1 plus 2, that is 3. So now we have come to 3C3, that is 1. Similarly, 4C0 is 1. 4C1 is 3 plus 1, 4. And 3 plus 3, 6. 3 plus 1, 4. And 4C0 is 4C4 is 1. Similarly, 1, 5, 10, 10, 5, 1. Similarly here, 1, 6, 15, 15, 20, 15, 6, 1. Then 7C0 is 1, 7C1 is 6 plus 1, 7, 7C2 is 15 plus 6, 21, and this is 35, this is also 35, because it is this plus 21 plus 7 plus 1 plus 1. That means adding the contents of the cells in the preceding row and the previous column, and in the preceding row and in the same column, we obtain the next value. If you recognize Okay, Pascal's triangle, and if you have heard about Pascal's triangle, okay, a fascinating mathematical structure usually studied in conjunction with the notion of combination. You are right, you are right, this is exactly that one, this is exactly what it is. Okay, this triangle which is generated is also called as Pascal's triangle. So this is rather simple when we compare calculating 7C3 through the direct formula. Therefore dynamic programming simply works and it gives us solution. So here, in order to obtain these two, we have overlapped the previous solutions. 1 plus 1 was added in order to obtain 2. In order to obtain this 3, we have added this one and this one, the previous solutions. Therefore dynamic programming essentially derives the final solution by overlapping the previous solutions. It could be addition, it could be multiplication, or it could be division. It depends upon the context of the problem and what exactly we need to find out. Anyway, dynamic programming is a technique that can be used to design efficient algorithms in terms of optimization while optimizing things. So we will write the algorithm. Okay, algorithm binomial coefficients. We need two parameters, that is n and k. N is very much greater than k. Okay, and both of them should be greater than 0. Okay, r can be equal to 0 also. Computes C of nk, combination of n items selecting k at a time by the dynamic programming algorithm, and the input is a pair of non-negative integers, n greater than or equal to k. Of course this is missing, greater than or equal to 0. Okay, that should be mentioned. Anyway, output the value of c and k, which is an integer, a positive integer. Now we will write the algorithm literally. Okay, for I should generate numbers starting from 0. As you once again recall your memory with respect to Pascal's triangle, it starts from 0, okay, towards n, it moves towards n till n do. This is the first for loop, okay, which will generate the rows up till n, and for j equal to 0 to, because C0 is possible, to k, it can go up to k, it can go to k, up to k, do. If in any iteration, if j equal to 0, the second term, j equal to 0 or j equal to I, so j equal to 0 will address 3C0, 4C0, something like this. J equal to I will address 3C3, 4C4, something like this. Okay, then if that is the case, if this is the case, then C of ij equal to 1. C of ij equal to 1. This is by the second formula. Okay, that's equal to 1, that we enlisted as a characteristic feature of this binomial coefficients. Else we will write the equation number 1, that's all. Equation number 1 says, okay, in place of n we use I, okay, because it is the first for loop which is generating from 0 to n, I comma j, C of I comma j equal to C of n minus 1, that is I minus 1, okay, I minus 1, k minus 1 means j minus 1 here as far as this loop is concerned, plus C of once again n minus 1, that is I minus 1 comma k, that is j. Okay, now we will return C of n comma k, return, that is nothing but the answer, that is nothing but the solution, return C of n comma k. Yeah, now we will see here is one comparison. If j equal to 0, okay, it's actually addition, but anyway comparison is taken as the basic step. Anyway, this comparison has to take place every time. Therefore, number of comparisons equal to, as a function of n and k, both the inputs are important. Okay, there are two input parameters over here. So one comparison within the inner for loop goes from 0 to k, while and this comparisons will be consuming equal to 0 to n. Okay, so many number of cycles. So if we expand this, it becomes k minus 0 plus 1, and this is to be summed up between the limits 0 to n, and it becomes k plus 1. K plus 1 is taken out, and this will give us n minus 0 plus 1. So n plus 1 remains. If you expand this, nk plus k plus n plus 1. Anyway, the higher order term is nk. Okay, therefore it belongs to the k. Okay, the dynamic programming based determination of binomial coefficients. Okay, this belongs to the complexity of big theta of n comma k, nk, that is called as quasi quadratic complexity. Okay, with this we will end up this simple session on dynamic programming. We gave an introduction for dynamic programming. We defined, we said that it is not programming per se. It is not like programming with using any high level language. It is way of thinking. Its way of thinking, or its way of planning how to get a solution by overlapping solutions available in the initial stages of the problem. It is not the small size of the problem. Anyway, it is the initial solutions. So any problem that is solved under dynamic programming strategy should have some initial solutions. Okay, then it can be overlapped meticulously in order to obtain a solution in total. So with this, we will end up this particular session, and the next session will bring out another example of application of dynamic programming, that is transitive closure of a graph. Okay, so there are many graph related applications of dynamic programming algorithm design technique. So with this, we will end up this particular session until I come back with next session on dynamic programming, next example on dynamic programming concept. Bye.